everyone, this is Miss Chelsea, and today we'll be learning about potential energy diagrams. Our question of the day is, how does a catalyst affect a chemical reaction? Currently working on two standards, SC4B, which is to construct an argument using collision theory and transition state theory to explain the role of activation energy in chemical reactions. Also SC4C, which is to construct an explanation of the effects of a catalyst on chemical reactions and apply it to everyday examples. So in chemistry, the energy stored in bonds, or the ability of a substance to react, is called the potential energy. We use potential energy diagrams to track the energy changes during a chemical reaction. Enthalpy is the heat of reaction. It is the total energy usage of the reaction, or the difference between the potential energy of the products and the potential energy of the reactants. We can calculate delta H, or the change in enthalpy, by taking the potential energy of the products and subtracting that of the reactants. In an exothermic reaction, energy is exiting the reaction. The energy is on the right side of the equation. That means that the reactants will have more energy than the products, and we will have a negative delta H. In endothermic reactions, energy is entering the reaction, and so energy is on the left side of the equation. That means that the reactants have less energy than the products, and we will have a positive delta H. Remember, activation energy is the energy needed to start or activate the reaction. Exothermic reactions are more stable and favored by nature because the end result, the products, have less energy than the reactants. Nature tends to be pretty lazy and not want to use that much energy, as well as pretty messy, and leans towards more disorder in the universe. There are a couple of important things to note. First of all, adding a catalyst will reduce the activation energy, which makes the hill lower. Let's do this by offering an additional reaction pathway. So, we've been writing chemical reactions as forward reactions. However, most of these reactions can actually be read both forwards and backwards. Hence, we have this little double arrow. Let's look at an example of a potential energy diagram for a reaction pathway. Let's look at the potential energy diagram of a reaction. The reaction coordinate is the amount of time that has elapsed from the reaction, and the energy is the potential energy. Notice how the reactants on the left have a higher potential energy than the products on the right. That's what makes this reaction exothermic. Because this reaction is exothermic, the delta H, the difference between those two energy levels, will be negative. So we have negative enthalpy. The reaction will actually occur at the top of this hill. So in order for the reaction to happen, then the particles have to overcome this energy difference between the reactants and the star. This difference is called the activation energy. We call that top of that hill, or the apex of the reaction, the activated complex. At this point, the chemical is reactants and products for a split second, so both are present. Let's look at another example of a potential energy diagram of a chemical reaction. Notice how here the reactants have a lower potential energy than the products. That makes this reaction endothermic. It also means that the enthalpy will be positive. Since the products have more energy than the reactants, delta H is positive. Notice how the activation energy of an endothermic reaction is much higher than that of an exothermic reaction. Activated complex is very tough to get to, which is why this reaction is considered not favored by nature.